Hi everyone. These are the examples that go along with the normal curve lesson. And in this first example, we're looking at the length of time that horses remain pregnant, the length of time that they carry their young. It says that it varies according to a roughly normal distribution, and those are always your key words here. That's what kind of gives you the go ahead to make all the assumptions that we're about to make. And then it gives you a mean and a standard deviation. So the first thing I'm going to do is sketch that curve. Okay? And I end up drawing this curve so many times in this chapter. But the center of my curve is the mean of 336 days. And then I want to draw lines to represent 3 standard deviations in each direction. Okay, a little asymmetrical, but it'll do. And so if the standard deviation is 3 days, that means that I'm counting up and down by 3. So this would represent 339, and then 342, 345. So it'll be 333, 330, and 327 days. Okay? And then in the video that you watched, it should have gone into how not only do we have that empirical rule that kind of tells you like it spreads out this far for 1 standard deviation and this far for 2 standard deviations, but if we just do some basic math, we can figure out what each one of these individual segments represents. You're going to want to make sure you have those numbers memorized. So like this section here comes out to be 34%. And this one is also 34%, because remember that first standard deviation represents a total of 68%. So we just took that and split it in 2. Okay. Your next chunk is 13.5%, and this is 13.5%. And so that comes from the fact that 2 standard deviations represents 95% of your data. And so if you take that and subtract out the 68% and then split the leftover by 2, you get the 13.5. Then we end up with a 2.35 here and here. And that comes from that 99.7 measurement, that within 3 standard deviations, 99.7% of your data shows up. And that leaves a tiny little 0.15 for the 2 tails. So really what this means is that people collected data on the length of times that horses were pregnant for a long time. And they arranged all this data, and this is what they observed, is that typically, 336 was average. We had some below, some above. But the great majority of horse pregnancies fell between 327 days and 345 days. There were a very small number that were less, a very small number that were more than that. Okay, so that whole idea of being within 3 standard deviations of the mean is really significant with a normal curve. So we're going to use this diagram to answer these questions. Between which 2 lengths do the middle 68% of all horse pregnancies fall? Well, the middle 68% is these 2 right here. So I would say between 333 and 339. Okay. How short are the shortest 2.5% of all horse pregnancies? So the shortest 2.5% would be really from here over. This is 2.5% if you do 2.35 plus 0.15. So everything from 330 down. You do want to make sure that you're representing this correctly. We don't want to just say 330 because 329 we also want to include, right? So we have to say somehow that it's everything less than 330 days. Technically, I guess it should be less than or equal to 330 days. The longest would just be the same thing on the other side. That would be these 2 sections here. And so everything greater than or equal to 342 days. And what percent of horse pregnancies last between 336 and 342? It's just a matter of putting all these percentages together. So 34 plus 13.5, and I'm just writing this down so you know where I'm getting it. Would be 47.5%. So 47.5% of all horse pregnancies fall between 336 and 342. And that should make sense because if we did that same amount on each side, that should be 95%. So if you split 95 in half, you get 47.5. Okay, let's try another one with heights of adult American men. And I feel like I've drawn this curve in particular a million times. Okay, so we've got our mean of 69, 3 standard deviations in each direction. And we're counting by a standard deviation of 2.5. So let's see, this would be 71.5, 74, 76.5. Going down, let's see, 66.5, 64, and 61.5. Okay, and same percentages apply. This would be 34, 13.5, 2.35, and 0.15. Same thing on the other side. Okay, so what percent of men are shorter than 64 inches? So here's 64 inches. We want everything to the left, and kind of like we just talked about up here, that would be 2.5%. I'm going to write down that we're doing 2.35 plus 0.15. So that would be 2.5%. What percent of men are taller than 71.5? So that would be everything from here over. So I'm really doing 13.5 plus 5 plus 0.15. Should give me 16%, I believe. Yep. The shortest 16% of men. Okay, so the shortest percent, now we know 16% on this side is from 71.5 over. So over here, we just want to take that same amount on the left side of the graph. So this right here would be 16% if I add these three up. And so the shortest 16% of men are anywhere less than or equal to 66.5 inches. So what percent of men are taller than 66.5? So let's think about this for a second. If 16% are at or below 66.5, then what percent are above 66.5? And if we're talking percentages, this is 100% total, right? So 100% minus 16% is 84%. I guess I should write down that that's how I did it. You could also take and add these all together, right? You could go 34 plus 34 plus, add all of those up, okay? And between what two heights do the middle 95% fall? Oops. That comes straight from our empirical rule. Empirical rule says up to 2 standard deviations is 95% of your data. So my middle 95% would be from the 64 over to the 74. So if your height is between 64 inches and 74 inches, you are just about as average as they come. Okay, 95% of men fall between those two heights. Okay, there's a very small percentage that are taller and a very small percentage that are shorter than that. And that's how we do the empirical rule. Okay, that applies again only to normal distributions, only when we know that the data is distributed normally, that we have one of these bell curve distributions, can we go ahead and apply this rule. Okay, I hope that was helpful.